So we've learned how to add vectors, subtract vectors, and multiply vectors by a scalar. But we haven't learned yet is how to multiply vectors. One vector times another vector. And there's two different ways to do this. One we're going to learn in this section, which is the dot product. A dot product is also known as a scalar product because the result will be a scalar, i.e. a number. Whereas the cross product, which we'll learn in the next section, will be called a vector product because the result is a vector. All right, so let's look at some motivation for why we need a dot product and what it can do for us. And one of the key ideas here is work. Now, work in a basic science class, we learn that work is force times distance, right? It's the force acting through a distance. There's your basic formula. Now, when we use that formula, we're making some very big assumptions that we are going to modify in this course, but you're assuming that your motion is in a straight line. You're assuming that your force, which is this, right? You're pushing on this box and you're pushing it along that distance from here to here. So you're assuming that not only is that motion in a straight line, but then you're also assuming that your force is acting in the direction of your motion. And then you're also assuming that the force is constant. Now, over time, we will play with all of these and make all of them go away because there's ways in Calc 3 to be able to deal with it when they're not true. But if they are true in Calc 3, then the work is equal to the magnitude of that force vector times the magnitude of that distance vector. But that's only true if the three conditions are satisfied. And that's a big assumption because most of the time for us they will not. All right, let's start by playing with one of these assumptions. We're going to make it so that the force vector is not going in the direction of the distance vector, that some component of it is, right? It's being pushed at an angle along that. So when you do that, let me draw the force vector over here because, of course, force vectors are free. It can be drawn wherever I want. There's an angle, theta, between the distance vector and the force vector. So that sets up a little triangle in here, right? There's two components to this force vector. There's the component that's going with the direction of motion, right? That's one piece of it. And then there's a component that's perpendicular to the direction of motion, which I have to find a color. There, I'll do it in green, right? That piece. So there's two pieces, right? There's the force that's going parallel to the direction of motion and the force piece that's going perpendicular. So if you will, this is the force vector piece that's perpendicular to the direction of motion, and this is the force piece that's running parallel to the direction of motion. And notice there's a little right angle here, and theta is right here. It's the same as over here. I'm just drawing the triangle on the other side, just because it's easier. I didn't want to mess up this drawing over here. So, but vectors are free, so I can draw it wherever I want. All right, now what is the force vector force component that is parallel to the direction of motion? Well, to figure out this component, we need some basic trigonometry, right? The cosine of this angle, the cosine of theta, is this piece divided by the magnitude of this piece, right? In other words, it's adjacent over hypotenuse. So this would be the magnitude of f times the cosine of the angle. And similarly, this piece over here would be, this would be the length of it, would be the magnitude of f times the sine of theta. All right, now how does that help us? Well, this is now the magnitude, if you will, of the force vector that's going in the direction of the motion. So if we take this piece, the work would be the component that's going in the direction of a motion times the distance vector, well, the magnitude of the distance vector. So we take, whoop, here we go, I forgot to put my magnitude sign in there, the magnitude of the force times the cosine of the angle. And that will get us the magnitude of this direction that's pushing in the direction of the motion. All the rest of this force is wasted. All right, so we just kind of rearrange that because we're mathematicians and we can't help ourselves. And it's the magnitude of the force vector times the magnitude of the distance vector times the cosine of the angle. And theta in this setup is the angle between your force vector and your distance vector. All right, so to recap, we broke down the force vector because the force vector has two components, the perpendicular part and the parallel part. The parallel part will be the magnitude of this force, right, the magnitude of the hypotenuse, times the cosine of the angle theta, right, because the angle theta is adjacent over hypotenuse, and the parallel piece is moving in the adjacent, or is the adjacent side. And that gives us our new way to multiply vectors, right, that we haven't had before. So we're going to take two vectors and we're going to do something called the dot product, and the dot product is working the same way that what we just found works, right? You take the magnitude of one vector times the magnitude of the other vector times the cosine of the angle that's between the two vectors. So even though we found it using work, it would work no matter what. All right, lovely. So let's use that definition. Oh, and for the record, it is commutative, right? So it doesn't matter what order we go in, because of course, multiplying the magnitude times the other magnitude, it doesn't really matter what order you go in. So this is commutative, and the result will be a scalar. It'll be a number. So let's do this, and let's see how it works. So we have two vectors. We have 2, 0, and we have a -1 square root of 3. All right, so 2, 0 is up here. Oh, no, it's not. It's this way. 2, 0. There we go. I went a little far. She got to 2. And then -1 square root of 3. Well, over -1 would be here. Square root of 3 is less than that, so less than 2, that is, right? Because, of course, the square root of 1 is 1, and the square root of 2 and the square root of 3 are in here, and the square root of 4 is 2, so it's this way. Wonderful. Okay, so we know that this component right here is -1, and we know this component is the square root of 3. All right, so using the Pythagorean theorem, right, 1 squared plus the square root of 3 squared would mean that this side over here is 2. Right? Little right triangle Pythagorean theorem. And so therefore, this side is the square root of 4, which is 2. So I could write it like this. Okay, I'll just make a little note. All right, so now if we want to multiply these two vectors, we want to do vector u times vector w. And this one was vector u. And, oh, this was v, sorry, not w, vector v. Okay, so u dot product with v would be equal to the magnitude of u times the magnitude of v times the cosine of the angle between them. All right, so let's see here. The magnitude of u would be the square root of 2 squared plus 0 squared, which is pretty straightforward. The magnitude of v we just found. It's right here. So it's the square root of 1 squared plus the square root of 3 squared. And then we need to multiply it by the cosine of the angle between them. Now, we don't really need to know the angle between them. We can kind of figure it out without knowing the angle, because we know that the cosine would be the adjacent over the hypotenuse. So the adjacent is -1, right? Because it's right here. So -1 over 2. I mean, the angle is right here, but we can use this triangle to figure out the cosine. So adjacent over hypotenuse. So we don't actually have to figure it out. So this is 2. This is 2, as we discovered. It's right there. And then the cosine of the angle, we just happen to know adjacent is -1 over hypotenuse, which is 2, and we're done. So we can just say that we can find this from the graph, right, with trig. Right? So we're using our trigonometry skills and finding that. And so then when we multiply, 2 times 2, which is 4, 4 times -1/2 is -2. Done. All right, let's find another one. So we have 3, 4, 3i, 4j, and then 7j. Okay, so 7j is up this way. It's actually past what the grid shows. The grid only goes to 6, so it should go up here. So that's 7. So that's the vector v. And then let me draw the vector u. I'll draw this one in blue. So over 3 to the x direction, up 1, 2, 3, 4 in the y direction. So it's like that. Now the angle between these ones is right here. There's theta. Okay, so again, let's think here. If I want to do u dot product with v, oh, I have these, my colors are backwards. Sorry, this is the u. All right, so u dot product with v, that would be equal to the magnitude of u times the magnitude of v times the cosine of the angle between them. Okay, so the magnitude of u, so let's figure that out. We know that this is 3 and this is 4, right? 3 here, 4 here. So the magnitude is the same as the length of that vector, and that would be the square root of 3 squared plus 4 squared. Which is the square root of 25, which is 5. So we'll do that in a second. And then the magnitude of v is really easy, because that's the square root of 7 squared plus 0 squared, or 0 squared plus 7 squared, whichever way. And then the cosine of the angle, I'm just going to leave there because we don't actually know the angle and we don't really need to know it. We'll be able to find this without it. Okay, so this piece is the square root of 25. That's 25 right there. And the square root of 25 is 5. So this vector here is length 5. And then the other vector is length 7, which we knew anyway because it's a straight vector with no, it's only in one direction. It's not, it doesn't have two directions. All right, so then the cosine of the angle. Okay, so we can see it here, we can see it here. That triangle's in two spots. It's the same triangle, right? So this is the opposite side, which is 3, and this is the adjacent side, which is 4. So the cosine of the angle will be adjacent over hypotenuse. Adjacent over hypotenuse would be 4 over 5. And there we have it. So let's think. The 5s would cancel, and we're left with 7 times 4, and that's 28. Notice our results for both of these. They are scalars, right? They are working out to be single number values. Right? So when we take the dot product, we're going to get a single number value. Notice also that when we do this Pythagorean theorem here, that's the same thing as finding the magnitude of the vector. And that's also going to be useful for figuring out the cosine. So it's doing kind of triple duty, if you will, right, or double duty, because it's definitely finding the magnitude and then it's definitely being used in the cosine piece.